All right, we're now ready to explore section 5.6, which is solving a system using matrices. So take a look. Again, keeping in mind we already have solved a system graphically by substitution and with linear combination / elimination. But now we're also going to add to that the idea of how to solve a system using matrices. And the reason for this, even though we got accurate answers, even though we have a good procedure to follow, straightforward, no confusion, the bigger combinations will be better. As we already found out in our 3x3 that we did with substitution and with elimination, they got really complicated. So if I suddenly gave you 3 equations, 3 unknowns, or even 4 equations with 4 unknowns, 5, 6, 10 with 10, maybe some problem in the future will have so many variables in it that you have to put it into a format like this. Think of it almost like a spreadsheet, and the spreadsheet would then help you do the math that goes with it. But the more variables you have, the more need here to use matrices. So that's the point. Ours won't be that big, so don't get scared off here. But we are definitely going to be solving systems using inverses now that we know how to do them. And for example, calculating business costs would be one place. So let's move forward. If we want to solve systems using those inverses that we learned about yesterday, we first have to be able to talk about how we get those. So let's go to just a little at a time here. Here's our system of equations. I have 2 equations. They're both linear. X plus 2y equals 5, 3x plus 5y equals 14. And now I turn them into a matrix equation. So notice there's a couple different parts. Over here, everything had to be in standard form before we started. So think standard form. Okay? If that's the case, then each of these components has a coefficient. Remember, the coefficient is the number in front of the variable. You have what we call a coefficient matrix. You then have the variables, x, y. And do this math for me. First row, first column. What do you get? Well, 1 times x is x. 2 times y is 2y. Added together, x plus 2y has to be our first term of 5. Oh, it actually works. We would get that equation from it. And simultaneously the second one. If I did second row, first column, I'd get 3 times x is x, plus 5 times y is 5y. 3x plus 5y adds together to give us our second row, first column item of 14. So there's our matrix version of that same system. So here they are. That first matrix that we had was called the coefficient matrix. We're also going to call it matrix A for discussion purposes. Then we had the next matrix, which was xy, which is the variable matrix. And then last but not least, we have the constant matrix. Some people like to call that the answers, but we'll call it the constants because 5 and 14 aren't going to change their value. So the coefficient matrix times the variable matrix has to equal the constant matrix. That's what our work will be. That's how you set the equations into matrices. Okay, so over here, what if we have a 3x3? That doesn't matter. Here's our equations. And you're going to say, well, some of them are gone. Well, if you ever have any variables that are gone, remember the only thing you can replace it with is like a 0. And make sure the order is the same. So if this is the A column, you got to have all A's lined up, then B's, then C's. So if they're all scattered and random, you need to order things before you start. So make sure everything's in standard form, then you can see what's missing. And again, down here, I don't have a B, so I'd have to sort of pad it with a 0. At least that's what you need for your thinking. So then my coefficients, look at them. 0, negative 1, 2 going across. 1, 1, negative 1 in the second row. 2, 0, 3 in the third row. And my variables are A, B, and C. So let's just try one. If I multiply the first row and the first column, I better get the first row, first column answer, which is a 4. Let's see. 0 times A plus negative 1 times B plus 2 times C added up. Well, that would be 0 A's plus negative 1 B's plus 2 C's equals 4. And that's exactly what our equation was up here. So it truly is set up correctly. Now, you have the coefficient matrix, the variable matrix, and the constant matrix. So over here, if we had questions, where would they be? Well, maybe in this top one. It's only two equations, two unknowns, and I'm missing something. So did you set it up as 3, 2, 0, 1 times a 2 by 1 matrix, which is just xy, should result in the answer 16, 5.
You need to go to the Lakeview parking lot, please. The minute lady for you.
Okay, from there, we have a triple that you could do the same thing with. So just practice rewriting just the equation to start with. Then we're going to go back and equate it to something we've already done. What do you mean? Well, if we now have a variable matrix A, which is the coefficient, a matrix A with the variable A as its name, X is our variable matrix, and B was our constant matrix, we have the same setup even just in a simple equation like 5x equals 15. So my question here is, what would we do in the common equation 5x equals 15 to get x by itself, to solve for x? And the answer most people would give me is, well, we'd divide by 5. Okay, great. And we'd get our answer. But the problem is, we can't divide. What do you mean we can't divide? Because we haven't divided with matrices. We've added, we've subtracted, and we've used scalar multiplication. So, we have only those choices. Oh, so now if I need to get rid of that 5, but I can't divide, what other choice do we have in our capabilities? And most people would then say, oh, I could multiply by the reciprocal. The reciprocal is also known as its inverse. So we're really multiplying by the inverse. That is the same as multiplying by the reciprocal. And if I did that, we would get that same answer of 3 that we had a minute ago. The only nice part is, with matrices, since we can't divide, this is the way we're going to have to solve them. We are going to have to multiply by whatever A's inverse is on both of these statements to get our result. Okay, so look at my work now specific to matrices. So if we have our matrix A, which is our coefficient matrix, and it's a 2 by 2, and then we have our matrix X, the variable matrix, which is a 2 by 1, and we're going to let it equal our constant matrix, which is also a 2 by 1. By following the process we just did on the previous problem, I can't divide to get rid of A. I must multiply by its inverse. And its inverse notation, remember, is A to the negative first power. Well, if I multiplied by its inverse on the left, remember, if its original is a 2 by 2, its inverse is also going to be a 2 by 2 matrix. So it's a 2 by 2. I'd also have to use that inverse over here on the right. Now the question is, can I put the 2 by 2 here or here? The question is, does it go in front or does it go behind to be able to multiply with matrices? And as you've learned with matrices, that the inner dimensions must match, and the only way the inner dimensions match is if the inverse matrix is in front. So we are going to have to put that inverse matrix, when we multiply by, in front of our constant matrix. Okay, we've got it. After we do that, notice inverses will cancel. All we will have remaining will be our variable matrix, and all we'll have remaining over here is that 2 by 1 that represents our final answer. And that 2 by 1 will equal this 2 by 1, and we will be good to go. We will know our x, y, a, b, and c, whatever the variables are, statement. So we need to do one with actual numbers. So sometimes you can find an inverse of the coefficient. You can use it to solve systems. So solving a system. So step 1, we were trying to write the system as matrix equations. So there is that same system. Step 2, we try to find our inverse matrix. And so in doing that, we first found out that our determinant was a 1. And then we did our flip the left diagonals values, switch them around, and turn the right diagonals to their opposite. In doing that, is that what you got for your inverse matrix? So we calculated the inverse, found it, used the determinant to help us do that. Once we did that, we now can come back to our equation and put our inverse in its correct position and do the math. So here we go. There's our inverse. There is the order that we have it written in. Here is the actual math with the numbers. Here is the inverse matrix with that constant matrix, and it should multiply out. So in the end, we should be able to say, with the multiplication there, that xy really is, that xy 2 by 1 really is the ordered pair 4, 1. So x equals 4, y equals 1 was our solution to this combination. What's that mean in retrospect to our problem? Remember, this was a system. If I have an ordered pair of 4, 1, it meant these two lines cross, and they cross at that ordered pair of 4, 1. So we have an intersection. So solve each system and check your answers. Now, it really doesn't matter, but I'd like to do an A-B just because we've done an XY before. So start off, and this is what I would like to see for how you would write these. So start off with changing your equation to a matrix system. So put your coefficients in, 5, 3, 3, 2. Your variable matrix, A, B, has to equal our 2 by 1, our constant matrix of 7, 5. Okay? Then off to the side or on another piece of paper, you can do your calculation. And I'm still working over here, so I do my determinant. 5 times 2 is 10. 10 minus 3, 10 minus 9. 3 times 3 is 9. Gives me a 1. So yes, I have an inverse. What is that inverse? I'm going to calculate it right here. The inverse of my matrix would be the two left diagonals switched. Remember, my determinant is 1, so I really put a 1 underneath each of these. I sort of skipped that step. But I flip the position of my left diagonal, and I make the right diagonal the opposite of what it started with. So when I complete this, I now have 2 lowest terms, 3, negative 3, and a 5. So my inverse is that matrix right there in lowest terms. So that will be the matrix I need to use to multiply. So on my next step, this is how I would like you to write it. You'll have that part on a separate sheet of paper. You know you're going to multiply by the inverse, if this is called the A matrix. And you know you're going to multiply by the inverse in front of that 2 by 1. Because remember, this is a 2 by 2, and this is a 2 by 1. So the inverse has to be in front. We know that's going to cancel. So just a little line. And that'll leave our AB on the left-hand side, our coefficient matrix. It will now have to be multiplied by the inverse, and I'm going to put that matrix down. 2, negative 3, 2, negative 3, negative 3, 5, times our constant matrix, which was 7, 5. So if I multiply this out, and that's your job at this point, I should get that matrix that is a 2 by 1 that represents my A and B values. Checking. We should have gotten a negative 1, 4 on the first one and a negative 2, 8 if you solve the second one. Right? So with that, the only other thing we need to talk about, well, what if we get a little bigger maybe? It's still going to work the same way. Solve the system. We still have constants, coefficients. So it's going to start going away. And you're going to set it up as a coefficient matrix times the variable matrix equals the constant matrix. You're going to now go to your technology, which I will have to show you in class what the step is, storing it on your calculator. But we should be able to store that matrix as a 3 by 3. So let's store this on our calculator as matrix A. Let's store this variable matrix as matrix B. Oops, sorry. Call that matrix B. And then this would be matrix C. So in reference of discussion, they said use B as the constant matrix. So I sort of screwed that up by not following directions. So let's just switch that up. And so A is the coefficient matrix, and B is our constant matrix. So this will be the only thing. And notice, we're going to be able to use our calculator, because that is a calculator readout right there, that allow us to do these 3 by 3s. So all 2 by 2s, we're going to make you do by hand. Anything that's 3 by 3 or larger, you will do with a calculator. So we will show you how you handle that with what you already know about matrices on your calculator. All right. So here is one that we will probably do tomorrow that is a 3 by 3 with our calculator to see what happens. Think we're good there? We could also use this for word problems. So here's a real world connection. A bead store has a sale on certain beads. Find the price of each size of bead. So right away you're looking at, well, I got different kinds of beads there. Well, you better start thinking if I have, let's see, 2 of these kind and, 3 of these kind, then I've already got a variable. Now over here it's 3 of this kind and on, looks like 4 of that kind. So be careful. You should be able to write your system. Check and see if you were thinking along these lines. We've got 2 large beads, 3 small beads for $3.25. In the second example, it was 3 large beads and 4 small ones for $4.75. We would let X be the price of 1 large bead. Let Y be the price of 1 small bead. Then we could write the system of equations that works with. So 2 times x, 3 times y equals 325 in the first row, first column multiplication. And 3 times x, 4 times y equals our 475, which is our first row, second column. We could then solve that by hand using matrices. Here's the work. First, figure out if we have an inverse. -4 times -2 is 8. 3 times 3 is 9. 8 minus 9 is a -1. We definitely have an inverse, so we work through that process. And we know that we're going to have to multiply our A inverse matrix times our B matrix. So remember, our B matrix has been our constant matrix right here. So after we did that, once we get that answer of $1.25 and 25 cents, we should know that the price, because that's what X was, price of the large bead is $1.25 and the price of the small bead is 25 cents. Here's another ice cream parlor one, another story problem. So we can do this. We might save that one for class. Now, last but not least, when the coefficient matrix of a system has a unique inverse, the system has a unique solution. Similarly, when the coefficient matrix does not have an inverse, the system does not have a unique solution. In that case, the system either has no solution or an infinite number of solutions. Now, this is basically saying that in our solutions, we usually got an XY ordered pair. We got things like lines parallel, so we would say no solution. And then we would get infinite because we had lines graphed on top of each other, and all points were the same, so we would say infinite solutions. Okay, as a quick reminder. So in matrices, you've got to be able to do that same thing. So if you get a solution, the determinant exists, you got that unique solution, that would be that XY ordered pair. But when you didn't get an XY ordered pair, they're saying it either has to be no solution or infinite number of solutions. And here's the big answer to that. They would say that when your determinant is 0, there is no solution. So you know when DET, your determinant equals 0, after you do the left diagonals product minus the right diagonals product and you get 0, then you know you have no solution, which means you have no intersections on whatever it is you're drawing. If it's lines, then you have parallel situation. Okay, you have enough information now to go forward. And the only thing we have to share in class is how do we handle matrices on our calculator that are bigger than a 2x2. So that's what we'll share in class. That'll take a little time, but otherwise we should have plenty of time for work on our problems.